This is Dr. S.P. Arsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 38 on the course of Strength of Materials, and this course is developed under the National Programs on Technological Enhanced Learning. Prior to start the lecture, we would like to discuss briefly about what we have discussed in the previous lecture. We discussed about the strut and the column, then how we can differentiate about this strut and column, and what the importance is there of the buckling load. So you see, we derived many things like in the different cases, like you see if the column or the strut is there with the pin joint, or you see with the pin and the fixed rigid joint is there, or completely rigid joint is there, or you see if there is a free end is there, then how we can get those crippling load and all. And then you see we found that there is a Euler theory is there, which is absolutely a computational theory, and using that particular theory we can simply get the crippling load that is known as the Euler crippling load. And also we found that if we have different modes of this buckling, then how we can get exactly those numerical values and how we can replace those things in terms of that wavy feature in this particular strut and column. So that we decide, and also that we discussed, and also we discussed about that what are the key factors through which we can simply characterize the properties of the strut. So that part you see we discussed in the previous lecture, and also along with that we discussed that if we are going in a realistic way, that means you see if we have an experimental part, then what exactly the difference is there in between the experimental and the computational theory of this Euler. Then we found that actually if we are doing in experimental way, then there is a failure due to buckling well before than what we have calculated in the Euler theory. That means you see whatever the assumptions which we made in the Euler theory, that wasn't correct. So we need to improve the theory. So that's what you see in the previous lecture. We suggested few of the modification in the Euler theory, like you see that we are considering the axial force exactly along the axis of this particular strut. But in realistic way, you see always there is some sort of eccentricity is there, and due to that eccentricity, what we have an additional moment is there in the strut. And you see when we are increasing the load, so with the gradual procession, we'll find that always this moment is playing a key role in the failure of this strut due to the buckling. So you see here in that particular modification, we adopted that additional curvature part is there, the R0, which is you see 1 by R0 is nothing but equals to d2y0 divided by dx. So this additional y0 is being added before you see any load application. That means you see we are assuming that actually there is a kind of deflection is already there in terms of y0, and then you see it can be easily added, and then in the whole theory we derived using this numerical values, and we found that it is pretty close to the experimental part. Along with that, you see we found that there is some with this eccentricity, some sort of nonlinearity is there which we are assuming in linear way. Like you see the first thing is that we have the material nonlinearity or geometric nonlinearity, means we are assuming that the strut is absolutely straight during the application, load application, but in realistic manner it is not like that. So we assumed you see all that kind of phenomena using straight line, parabolic path, or whatever you see and then we found that after application or after inclusion of all these theories or all these the modification, we found that we are pretty close to these things. So with those inclusion, you see we discussed some of the issues in the previous lecture, that you see if both the joints are pin joint, then you see how we can develop with a modified way. So along with all these discussions, now in this lecture we will start from that if we have the strut with the pin joints or whatever, then how we can refine those things. So these are few of the cases which we discussed, and also we would like to discuss one more case, and then we will go with some energy methods, that you see if we have a kind of any solid mechanics, then what exactly the energy methods are there in those things, and what are the associated terms are there, and what is the physical and their relative terms are there, and the physical significance is there in order to check it out those property, and in order to check it out the failure theories of the object, or we can say the solid mechanics part. So you see here in this lecture, as I told you, we are continuing with that strut part with eccentric loading. Because you see as I told you in the Euler theory, we are assuming that there is no eccentricity is there, But in realistic way, we'll find that there is always a kind of eccentricity is there, because when we apply either the compressive or any kind of load, it is not exactly in the same like the streamlined, or we can say the centroid of the particular strut. That means you see like we need to introduce some sort of eccentricity to get the real feeling of the strut in experimental way, because as I told you in a few of my lectures that whatever we are discussing about the real nature or the experimental part, all real systems are highly nonlinear or highly complex in the real nature. So if we want to predict the failure theory or behavior of those kind of systems, we need to be very close to the real nature. That means you see we need to introduce some sort of the nonlinearity, or we can say this kind of eccentricity. So you see here, if you are saying that you can look at on this particular screen the figure, it is simply a strut is there, the pin joints are there, and we have you see like simply introducing here the eccentricity E, which is like at the particular applied load part. So here you see like this load is being applied here, and we have an eccentricity E part here at this particular point O, and just we are measuring Y obviously in this whatever the deflections are there in longitudinal direction, and then you see this strut is flowing in this transverse direction is there. So along with these longitudinal and transverse direction, we would simply find our main intention is to find it out that what exactly the impact of this E is on that particular this behavior of our strut. So again you see the same procedure is there which we discussed in the previous lecture. What we have the strut is there, and then you see the total length of the strut which we are assuming here is L, and then the same elastic properties are there. So modulus of elasticity is E, and this area moment of inertia is I is there. So we can simply calculate the flexural rigidity for this EI, and then you see like again the same 2 degree, the second degree of freedom is there. So that's what you see we have like the second order differential equation is there. So again if we want to write in the derivational way, so then we have you see like d square plus n square into y is equals to 0. So what we have d square is nothing but equals to d2 square divided by dx square, and n square as usual you see we have p over ei. So we have the second order equation, so obviously we have the generalized solution. So in that you see we have the complementary function is there. So if you want to calculate the complementary function, same procedure is there, a sin x plus b cos x is there. So again you see since it is simply flowing with the n, so we have a sin nx plus b cos nx is there as a generalized solution. So you see we need to apply like to get the coefficient value a and b, we need to apply the boundary conditions. So after applying the boundary conditions in the pin joint where the load application is there, only the key feature is that we have eccentricity at point O, while at the other end of this particular pin joint there is no eccentricity is there. It is exactly, we are assuming that it is exactly at the centroid of this strut. So with those conditions what we have you see like ei into d2y by dx square is equals to minus p times y, the simple theory you see which we discussed. Now with the boundary conditions at the x equals to 0, y equals to e, that means you see already we have even this eccentricity might be in terms of microns or even in terms of millimeter, but it is present at x equals to 0. So obviously you see we have now this time b has some value, so b is equals to e, and if you are keeping x equals to L by 2, there is no slope is there because the maximum deflections are there, so dy by dx is equals to 0. So keeping those values at x equals to 0 and x equals to L by 2, we have a cos n L by 2 minus b sin n L by 2 is equals to 0, or we can simply calculate the a which is equals to b times b into n L by 2, and you see here we already calculated the value of b which is eccentricity E is there. So we have the coefficient a value is e times 10 of n L by 2. So you see here what we have the complete solution in terms of y is equals to a sin nx plus b cos nx. So if we are keeping those values a and b, what we have the complete generalized solution of the equation in which you see the pin joints are there but the eccentricity is there. So it is eccentricity is also playing a key role in the generalized solution. As you can see the equation y is equals to e times, so you see here this e is present exactly in the basic term of the solution. So you see how great influence of this e is on the generalized solution. And you see generally in the Euler theory we simply ignore this term. So that's why you see, like whatever the failure, the buckling load is coming and the failure is there, there is a great difference because we were ignoring this E in that case. But with the consideration of E, now we are very much close to the real nature of the failure, so that whatever the prediction is there about the failure theory due to the buckling, it is pretty accurate. So y equals to E times 10 into NL by 2 sin nx plus cos nx. Now you see here, we have like the complete equation or complete solution is there of that. Note that with an eccentric load, the strut deflects for all values of P, not only for the critical value as was the case with the axially load applied. That means you see the deflection becomes infinite for 10 NL by 2, which is equals to infinite, or we can say that NL is equals to P, giving the same crippling load. So you see here, means it is valid for almost, you see, 10 into NL by 2 to the infinite part. So if we are talking about a general case, then we'll find that the this eccentric load, under the eccentric load is the strut will deflect not only for the critical load values, but also for a variety of the values. However, due to the additional bending moment set up for the deflection, because you see there is always, due to the eccentricity, we have an additional bending moment is there, and we need to consider in order to calculate the real value of this buckling load. So the additional moment is being added up, and the strut will always fail by compression stresses before failure the Euler load is reached because of the additional part. So you see here what we have the crippling load of Euler, P is equals to pi square EI by L square, and you see if you are calculating the P for buckling load failure, if PE, then you see the value is quite maximum, but you see we need to add up something, as we discussed just now. You see that the additional bending moment has to be added in this case. So now come to the main point, the generalized solution y was equals to E into 10 into NL by 2 sin nx plus cos nx, or we can say that now we have the real values of this. So we have the maximum at x equals to L by 2, the deflection is there because it is exactly at the center position. So we can say that E into 10 NL by 2 sin NL by 2 plus cos NL by 2, or we can say that if we simply manipulate those things, when we have sin square NL by 2 plus cos square NL by 2 divided by cos of NL by 2. Simply we need to change this 10 by sin over cos, and that's why you see sin square plus cos square, that is 1. So we have the maximum deflection, which is exactly at the midpoint of that particular strut, x equals to L by 2. We have the value 1 by cos cos of NL by 2, or we can say that E times of sec of NL by 2. So the maximum bending moment in this case would be exactly equals to a maximum which is due to the axial load P into y maximum. Or we can say that now, since we know the y maximum, which is exactly at the center point of the strut, so we can simply replace in this particular value, and we have the maximum bending moment in that case is P into E into sec of NL by 2. So now the maximum stress can be easily obtained by combining direct, combining those things with the direct strain. So what we have, because you see we know that there is an additional moment is there of this nature, so we have sigma, which is P by A due to the stresses due to the axial loading plus stresses due to the bending moment. So the total combined stresses which is in the nature of the maximum stresses are P by A plus M by Z. So stress due to bending moment is pretty common, that is sigma by y is equals to M by I, or we can say M is nothing but equals to sigma into this I by y, or we can say that I by y we can simply replace by the section modulus of the elasticity. So we can simply replace sigma maximum is M by Z. So by keeping this M by Z, we have the combined stress, the stress is there, but we have a real feeling that whenever strut is there under the action of these axial forces, it can be the buckling load can be easily calculated with the using of two main impact. So if you are talking about the stress, then we have the two main component in that. One is due to the bending moment M by Z and one is due to the applied load is. And that's why we have a clear feeling that the second term is coming because of the bending action is present in that, which we were ignoring in the basic form of the Euler theory. But in this case now we have the bending action is there and the axial action is there in that case. So consider a short strut subjected to an eccentric applied compressive force P at its upper end as shown in the first diagram. If such a strut is like comparatively short and stiff, the deflection due to the bending action of eccentric load will be negligible as compared to the eccentric E, and you see the principle of superimposing applies. That means you see here, if the strut is pretty short and it is very stiff, then this eccentric due to the bending moment due to this particular eccentric load having less impact. So in that case, you see like somewhat this Euler theory which we derived is comparatively okay. But you see, when we are talking about somewhat the column part, that means you see somewhat like even the short distance is there, the short length is there, but it is not much stiff. Then obviously you see there is a kind of like the curvature part is there because of less stiff part. So then we need to consider like the m by z as an additional component, because the bending moment is always applicable because of the eccentricity. So you see here like these theories are always somewhat having a real feeling about what exactly is going on with the kind of strut or the column. But if the strut is assumed to have a plane of symmetry, that means you see it is simply in their xy plane is there like that, and the load P lies in this particular plane, like you see we are considering at a distance E, then like we need to consider this the impact of this eccentricity, and that's what you see exactly it is following the centroidal part of the axis O, and then in such a case you see the loading may be replaced by its statistical equivalent centrally applied compressive load, which we can simply shown in the next diagram, because you see like we know that since this load is exactly not at the centroid part, but somewhat you see it is displaced by point E, so there are two main impacts are there. So you can see in this diagram, this you see like we have the structure simply like this is there, and it is simply flowing along the x direction. Simply this is the rigid part is there, and when the load is not, and this is the centroid, you can see this particular center line or which the centroid is there. So instead of keeping the load at centroid, if it is, let us say it is being displaced by E, as I told you, so it can be replaced by two main things. One, you see the load is there, so you shift the load at the center point. So like you see we need to shift this P load at this particular center point. So this is the center point here. Along with that, we have the moment which is coming due to this eccentricity, and this moment m is nothing but equals to P into E, and this has a nature in the clockwise direction. That means you see this moment is always tending to move this particular element in a clockwise direction. So like we have the two main this components are there. If eccentricity load is there, one is the axial load, that is P, which we are considering and assuming that actually it is now on the centroid part, and second is there due to eccentricity we have this bending moment which has the magnitude P into E, and now this bending moment will tend to move this object in a clockwise direction. And then you can see that you see the nature, what the tendency is there. So if you look at this particular only axial load, then only it is just going or we can say it is simply flowing with the flow of this axial load. But while you can if you check it out the bending moment, now you can see that at this circumferences we have the maximum value, but like because the tendency is just to move the circumference of this particular way. So if you combine those things, then the eccentric loading will give you the real feeling of the load is like that, with the straight and having tendency at the maximum of the circumference. So this is you see the real feeling of the eccentric loading is, and that's why you see like the centrally loaded applied load P produces the uniform compression, as I shown you the sigma 1, which is P by A stress, of which each cross section has shown like having the same stress diagram is there with the uniform way. While you see the end moment, this bending moment is there m, produces the linear varying bending stresses sigma 2, which is m y by I, or we can say m by z, as shown in the other figure you see. And if you combine those things, then we have like the superimposition figure is there, the total compressive stresses in any of the fiber due to the combined loading of bending as well as the compression. We have, you see, sigma is equals to P by A plus m y by I, or we can say that sigma is equals to P by A plus m over 1 this I by y, or we can say sigma, which is exactly like the real value is there, which is P by A plus m by z. So this is you see like the real procedure to calculate when like the eccentric loading is there in the strut, and it is simply applied along the axis but keeping some eccentric part, and due to that you see we have an additional component of the bending, and that's what you see like in the particular strut part. Always when we are going for experimentation, it is always fail before the Euler crippling load, because of this object was missing in the Euler part. So you see here in that particular theory, this is all like we discussed about the strut and everything you see now. But we found that actually there are some of the key parameters which were like absolutely missing and which has to be focused. So that's what you see now. We pick up some of the part here, and that's what it is, starting with the energy methods. In that you see we have variety of categories, and we would like to see that what are the important like the energy parts are there, or the terminologies there, which is very much closely associated with the kind of material property, and how they have an important influence for designing these materials when they are subjected by a force application. So starting with the strain energy, we have like the strain energy of a member is defined as the internal work done in a deformation in the deforming the body by action of externally applied forces. So when you see the load application is there, or a point of application of the force is there, we need to see that actually what the kind of deformation is, and whenever the deformation is there, that means you see when there is an external excitation is there, the energy is being transferring. So where is this energy is going? So the energy is absolutely absorbing by these objects, and this energy in the elastic body is known as the elastic strain energy. So if you look at this particular uniaxial loading part, we have like a kind of cube. So you can see that there is kind of, you see the sigma axis there, that means the axial forces are there in the x direction. So like the stress component is there along this particular x direction in a tensile way. So sigma x and sigma x is going in this way, sigma y, sigma z, and like all these the small segments are there. And if you are like going for an infinitesimal element of a dimensions of dx, dy, dz, then our main focus is just look at the sigma x. So you see here this now like the forces which are acting on the face of this element is tau x dy, like because the stresses are just in that particular this x axis form. So we have, you see, the different kind of forces tau x into dy into dz, because you see the domain of the force in the x only. So the area is dy dz, and you see the shear stress is there, which is a plane stress. So obviously the force, the shear force which is there on the x face is this tau x into dy into dz, where dy dz is the area of the element due to the application of forces. An element deforms to and about is this, you see, whenever the deformation is there under the action of any force is epsilon x into dx. So this is, you see, like the deformation is there, and in that epsilon is nothing but the strain in the material in the x direction. So obviously it is nothing but equals to the ratio of change in length divided by the original length. So now what we have elastic deformation, and in this elastic deformation, now you see here when the load application is there, we have certain kind of deformation. So that means, you see, when applied load is there in the x direction, the kind of deformation is there. So we can straightway define the strain energy in this way. That means, you see, like the strain energy is nothing but equals to half of sigma x into epsilon x. So sigma x is coming as the natural, like the normal strain component, the stress component due to the action of force, and due to the action of force, the deformation is there, which is to be computed in terms of the strain. So epsilon x is there, and both are equally responsible for the kind of strain energy in an object. Now assuming the element material to be linearly elastic, so you see here all these theories are pretty close to that what exactly you are assuming. If you are assuming that the load is only applied up to the elastic deformation, that means, you see, whatever the relations are there in between, say stress, strain, or you see whatever the other terms are there, like Young's modulus of elasticity, shear modulus of rigidity, or whatever you see, they are absolutely valid. And in that case also we have a linear elastic, like the stresses are there, which have it, which has, you see, like the directly proportional terms are there with the strain and strain. And you can see here in that particular figure that we have, you see, the stress strain diagram, and in that there are two main type of energies are. One, the downward part of the straight line, that is the strain energy, and another one is there in the recovery form is there, means on the top of side, in which you see, like we have the base of sigma, and the domain is sigma, and the base is tau. So in that case, you see what we have the complementary strain energies there in that case. So you see here both are there, but the part of, you see, like the lower part is strain energy and the upper part is the complementary energy. We can also there say that the complementary strain energy in that case. So average force on an element is obviously, you see, since if we are talking about the average, because we are assuming that again the very important aspect is we are assuming that the force under the action of the force stress distribution is uniform along the material. So hence we can say that the average force on the element is half of sigma x into dy into dz. Therefore, you see the work done on above force is like this, obviously it is always coming due to the average force into the deformed length. So half into sigma x dy dz into epsilon x into dx. So now you see like for a perfectly elastic body, the above work done is like the internal strain energy. So du can be easily calculated, because is whatever the like the work done is there, this work is being done by the application of force, and the total energy is the equal amount of energy is being stored within the element. So we can straight, and that too you see we are always considering that it is elastic body, so we can simply replace this work done by the strain this internal strain energy du. So du is equals to average force into the deformed length, or we can say that half of sigma x into dy into dz. So this is you see the force, and we have the deformed length, that is epsilon x into dx. So by combining those terms, we have half of sigma x epsilon x into the whole unit volume of this element. So we have dx, dy and dz. And if you are talking about the du, then we have half of sigma x epsilon x into dv, or we can say that the strain energy per unit volume is nothing but equals to sigma x epsilon x by 2. That's what I told you. That if you are talking about an elastic body, then the stress sigma x and epsilon x strain is equally responsible for the kind of strain energy storage. So you see here, and since you see the strain energy is having the domain of volume, so that's what you see the du is always calculated as half of sigma x and epsilon x into the dev, that what exactly the volume is there and how it is being deformed under the action of applied load. Where you see dv is nothing but equals to dx, dy and dz, which is you see the volume of the element. So by rearranging those terms, what we have like the u0, or we can say the du by dv is nothing but equals to half of sigma x and epsilon x. So this equation represents the strain energy in the elastic body per unit volume of the material, and like its strain energy density u0. But that means you see like when we are saying that it is per unit volume is there, so we can say that it is strain energy density, that is u0 is there. And since we are considering only the elastic body, so obviously whatever the deformation is there, this is absolutely under the Hooke's law. So for Hooke's law, the elastic body, it can be simply sigma is equals to E into epsilon, where E is the Young's modulus of elasticity is there. So with that consideration, now what we have, and since you see like there is a linear relationship is there in between the stress and strain, and you see like it is directly proportional is there, so we can simply replace this equation in that particular form. So what we have u0, which is du by dv. It can be simply replaced by sigma x square divided by 2e, or we can say that since the sigma is nothing but equals to E into epsilon, as we can see in the first previous derivation, so we can simply replace E into epsilon square by 2. So you see here now, since it is like the elemental part is there, so if you consider whole body, so you need to simply like integrate that part, whole small segments are there. If you integrate in that particular same domain, so we have you see the internal energy is equals to the strain energy within that internal part is equals to the integration of whole volume into sigma x square divided by 2e into dv. So within the volume domain, you can get the total energy by summing up or by integrating those terms. So in the case of a rod of uniform cross section subjected to its end, an equal and opposite forces is being there. So now you see here, after like going through from this particular internal energy, we have a clear feeling that whatever the load application is there, like you see in that particular diagram in front of you, we have equal and opposite load is there. So we know the P. Once you know the P and you know the cross sectional area, that is you see the A is there, what you have a straight like these stress components are there. You know the material property, so you have the value of E. So sigma x square by 2E, and then you see what the domain is there of this particular element. That means if it is a cylinder, if it is you see the cross sectional area is a square or any rectangular, simply take the volume of that and calculate what exactly the strain energy is there of whole element. So you see here for this particular diagram now we can simply calculate the strain energy as this U is equals to integration of this volume with this particular L sigma x square by 2E into dV, or we can say that since if we absolutely replace from that particular area part, because you see in this particular cylindrical part it is pretty easy to calculate the area, and since area into dx will be the volume, so you see here the U which is 0 to L this sigma x square. So sigma x is now replacing with the force because this axial stress is coming due to the application of force. So this sigma x is now P by A. So if you are replacing this sigma x by P is equals to P by A, we have P square by 2E into A square into now dV. dV, since we have a cylindrical element, so obviously it can be easily replaced by area into dx, because it is simply like varying the length in the x only distance. So we have dV is equals to A into dx, which is the elemental volume. So we have, you see, P square over divided by 2E into A square into A times of dx. So with the manipulation, what we have the strain energy for that the simple like the cylindrical element in which the axial forces are there. We have P square L over 2 times of A into E. So if you look at this particular point, then you will find that the 2 or 3 like the parameters are really like the importance to calculate the strain energy. One is that material property. What exactly material which you are using, because you see whatever the load application is there, if material is more stiff or material is less stiff, accordingly the deformation is there, and then you see we can say that yeah, it can be deformed like that. So it may be having, you see, the more and more this elastic the strain energy is there in the elastic form. Second property is the area, that what exactly the dimensional part is there, means actually what exactly like the cross sectional area is there. Correspondingly, you see the energy storages are there in the fibers of the layers. And third, which is more important part, is and directly related to the strain energy, is the load. Maximum load is there, maximum, you see, the deformation is there, and there is a great chance of having the strain energy storages. So that's what you see. If you are checking out the U, then U is like equals to P square. So it is in the terms of the P square is there. So these are, you see, some of like the main parameters are there through which we can say that we can simply calculate the strain energy if we have any kind of element. You see, simply like we need to calculate the area, we need to check it out what the material is there, corresponding Young's modulus of elasticity is there, and just like we know the length and just the load according to the varying load, we have the different elastic energy, or we can say the strain energy in the elastic forms. Okay, so in the first part of that, we discussed about the strain energy, in which we found that like these are the key parameters to calculate the strain energy of any of the element, irrespective of whether it's a size or material or whatever. Now you see here the second part is the modulus of resilience. Now suppose, let us say, if we have the sigma x in the strain energy equation is put equal to sigma y, that means the stress at stress at proportional limit or yield limit is there. So that yield point is coming now, and the stress is approaches up to that point, which like clearly defines the limit of elastic and the plastic region. The resulting strain energy gives an index of material ability to store or absorb energy without permanent deformation. That means, you see, now we are approaching up to the maximum value of like the strain part up to the elastic limit. If you go beyond that, then there is a certain chances there of the kind of elastic deformation. So up to that point, whatever the stored energy is there or whatever the absorbed energy is there, that is is considerable. So the quantity which is like coming up to the this yield point resulting from the above equation is called the modulus of resilience. So you see here this limits this absorbed energy, or we can say the stored energy limits the elastic region and the plastic region. So we can say that actually if the stored energy is up to that particular point, we have an elastic region. So within that, you see now the different form of energy which is known as the modulus of resilience is always shows that the stress is there up to the elastic limit, and this, you see, can be easily calculated. Uy is equals to sigma y square divided by 2e. That means, you see, the stress up to the yield point sigma y divided by 2e, and then you see this energy is absolutely depends on how much force application is there up to the yield limit and what is the elastic property is. So now you see, if you want to draw these things, you can simply limit that particular part, that we have a simple tensile test, like a diagram is there, the stress strain diagram, and like one of the key feature is there in that we always draw the stress and strain in this way. Can you tell me why you see the stress is always being drawn on the y-axis and the strain is there on the x-axis? The basic reason is the strain is always a measurable part and the controlled part. Let us say, you see, if you want to check it out, we apply the load and we just want to check it out that how much stress induction is there if we simply go up to the deformation of 0.1 millimeter or 0.2 millimeter or 0.1 micrometer. We can simply check it out. So it is a measurable part and it is a controllable part. So that's what you see, whatever, just like you see the time displacement is there, or time velocity is there, or the time acceleration is there. Always time is coming on the x-axis. So which domain in which you want to analyze those things. So here also our domain is how much deformation is there, what is our parameter is there of the deformation is. So that's what you see here on the x-axis or on the x domain, always the controlled and the measurable part is coming, while the dependent part is always coming on the y-axis. So similarly, you see, come to this point again, we have a this modulus of resilience is there. So in that case, a simple tensile test part is there, and you see now we just, it's a very straight diagram is there, that when you start the loading, it is elastic deformation, and then you see the yield point is coming, upper and lower yield point is there, and then the nonlinear relation starts forming. So in the nonlinear relations, now the sigma, which is not directly proportional to the epsilon, that means the stress is not directly proportional to strain, then you see all those, you see the the maximum tensile strength is coming and the failure is there up to the end. But we are talking about, you see, when it limits the yield, the elastic deformation region. So this is the yield point is there. So up to this, if we apply the load and you see the sigma is approaches to sigma y here, you see whatever the area under the curve, that means whatever the energy is being absorbed by the material under this particular load application, this shaded area is showing the modulus of resilience. So you see this modulus of resilience limits the elastic region, and then you see we can say it limits the linear strain region is there with the linear stress part. So this is like the second term is there. Now the third term of the energy is the modulus of toughness. Now suppose you see the strain, the epsilon, in the strain energy expression is replaced by epsilon r. That means you see the strain at rupture or the failure. That means now we are talking about the nonlinear relationship between the stress and strain. And this strain is now you see the replaced by the strain at the fracture or the rupture. The resulting strain energy density is called the fracture modulus of toughness. So now this is the reason is slightly shifted. Earlier you see we simply like in the modulus of resilience, we simply keep the region within the yield point only from the starting point. Now we are going up to the rupture point. That means you see it includes both elastic as well as the plastic deformation. So from the stress strain diagram which I shown in the previous one, the area under the complete curve gives you the measure of modulus of toughness, that how tough material is, and it is the material ability to absorb the energy up to the fracture. So this is the key difference between you see this from the this modulus of resilience and the modulus of toughness. So you see here from all these terms, what we have concluded, we simply concluded that even if we are talking about the strain energy, we need to start from the basic element, integrate those things, and we can get that part. And then another, you see, we can simply segregate the total curve of the stress strain diagram simply by two terms. When we are talking about from this starting point to the yield point, means the elastic region, the modulus of resilience is there, whatever the energy is being absorbed up to the load in the elastic region. But if we are going up to the fill, whatever the energy is being absorbed by the material, this energy is being known as the modulus of toughness. And you see in this diagram you can simply see that this is the strain diagram, this is the elastic region, you see the directly proportional region, straight line region is there, we can say the linear region, and this is the nonlinear region, and up to this you see we have the rupture. So you see whatever the energy is which is being absorbed under that, this will give you the modulus of the toughness. And if you want to calculate up to that, then we have you see u, which is integration of 0 to e So this E into this epsilon x into dx, or we can say that since now this epsilon x is being replaced by epsilon r, so E into epsilon r square divided by 2 into dv, the whole volume now, because up to the failure it is there. So we have u, which is, you see, the modulus of toughness is equals to E into epsilon r square divided by 2. That's what, so that's what you see here. Again, in the modulus of, the toughness, the material property is very important. The E, the Young's modulus of elasticity, is there, and the second is there that how much deformation is there at the rupture epsilon r. So the strain part is there at the epsilon r is there at the rupture point. So you see here, these are the two key parameters for calculating the modulus of toughness. And then you see, you will find that these two main parameters which are really having a great influence of these things. So you see, this is the another reason of the modulus of toughness, and the first one was there, the modulus of resilience. So you see, these three parts which we discussed, right from the strain energy, the modulus of resilience, and the modulus of toughness, we simply categorize these energies as that how much the energies are being associated according to the application of load, and what exactly we want. We want only the elastic deformation, we want plastic deformation, and we just want to see a kind of deformation and how much load is applied is there, and what the total the stored energy is there within the particular volume domain, that will give the strain energy. So these three basic forms of the energy were there, and we discussed all this part. Come to the now some of the numerical problems. So the first numerical problem we have taken up, and you see this problem is, we have the three rounded bars having the same length. So you see all three bars are having the same length L, but the only key change is they have the different shapes. I'm going to show you in the next slide. The first bar has the diameter d, or its entire length. So you see, it has the uniform cross sectional diameter is there, and then you see it's simply the diameter d is there. The second had its diameter over 1/4 of its length, and the third one is the diameter over 1/8 of its length. So that's what you see. Now they have given the same relation with the diameter and the length, and you'll find that they have the different kinds of shape with the length and diameter ratio. All three bars are subjected to the same load P. That means, you see, the external excitation is the same. Compare the amount of strain energy stored in the bars, assuming that we are simply applied the load within the linear elastic region only. So that's what you see, in that they are behaving as the linearly elastic one. So the same diagram, you see, we have all three bars. One is the straight cross uniform cross section is there, load application P, and this is the diameter d is there. And then you see again this is the second one which has the same length, there is no change in the length, and the applied load is P, but there is, you see, the dip is there in between that. So the first diameter is 3d, last diameter is 3d, but in between you see the 1/4 of length is having diameter d only. Then you see we have 1/8 of length is just diameter d, but other parts are thrice of that. So 3d and 3d is there in the remaining two regions. So you see, if you compare, we'll find that this is the entire length L is having diameter d, 1/4 of this length is diameter d, and 1/8 of this length which is having the diameter d. Then you see here, now what we need to do, we need to simply go with the same, because we want to calculate the the energy. So the total strain energy for the first bar is pretty simple, because you see we have straight relations. So U1 is P square L by 2 EA. As I told you, this strain energy is absolutely depend on what the load application P square is there and E into A. So this is very straight. You see, simply by keeping the values you can have the strain energy of that bar. But the second bar is very important, because you see it has a different altogether, you see the reasons. So the strain energy in the second bar can be simply expressed by the two different way. One is with the diameter, in which the d diameter is there, so that length is L by 4, and another one in which the diameter is we have the 3d. So you see corresponding area will be changed, and the total length of that is 3L by 4, because you see when L by 4 is going into the d diameter, 3L by 4 will be there with the 3d diameter. So U2 is first for L by 4 this length in which the diameter is d, we have this P square L by 4 2 into E into A. So A, say let us you see it's a simple uniformly cross sectional bar, so pi by 4 d square is there. But now you see here in the other term we have this 3d diameter is there, so obviously the area will coming up with the 9 times of the previous one. and the total length is 3L by 4. So we have P square 3L by 4 into divided by 2E 9 times of A. So that's what you see, if you compute those things, then we have the total P square L by 6 times of EA. So means that you see, if you simply increase the diameter, the strain energy storage is 1/3 of the previous one. So you see, it has a clear meaning that even if you increase the diameter of the bar under the same load application, the deformation is quite less, and then the stored energy is somewhat you see like the 1/3 of the first one. Now come to the third case, in which you see only the 1/8 of area is having diameter D and other diameter is being increased by 3D. So that means you see 1/8 is there, and the 7/8 the diameter or the length is now having 3D diameter. So come to the total strain energy for that particular reason. What we have U3, which is P square divided by 2EA into L by 8. So this is the 1/8 area where the diameter D is there. And now you see P square 7 times of L by A divided by 2E. Now since the diameter is 3D, so we have the 9 times of A. Compute all that part. What we have U3, which is equals to P square L by 9 times of EA. So U3 is nothing but equals to 2 by 9 U1. So you see here, means if you again reduce the this particular length with this particular the diametric changing, we'll find that the number of with the increasing of the diameter, the total stored energy within that element under the same load application is somewhat reduced by 2 by 9. So you see here what the great influence is. Initially you see it is being just reduces by 33%, then now it is being reduces by 22%. So you see here, when we are increasing or decreasing the diameter, what the great influence is there of the stored energy or the strain energy under the same load application. This is of a great importance, that how stiff that part is. So from the above result, it may be observed that the strain energy decreases as the volume of bar is increases, and then you see if we want the significance of this strain energy, accordingly we will take the cross sectional part of these elements. So this is you see the difference between a uniformly cross section bar and the non-uniform cross section of bar. Now we are going with the second numerical problem. Suppose we have a rod AB. You see this rod AB is there, and it must acquire an elastic strain energy of 13.6 Newton meter with the using of Young's modulus of elasticity 200 gigapascal. Now we need to determine the yield strength of the steel if you see the fracture just we are going up to the rupture or fracture up to that, and in that the factor of safety which we are considering under the permanent deformation, the fracture which I have talking about, is equal to 5. So we need to take the factor of safety 5 to reduce avoid the rupture or the fracture of this failure part. So now you see we are going with that. Now since the factor of safety is given already a 5, and then you see now we would like to calculate to see that what exactly the yield strength is for which the strain energy is given as 13.6. So you see here now the strain energy of the rod, it should be now this U, which is equals to 5 times of 13.6. That means you see, to avoid the failure with the using of this much factor of safety, we should have the strain energy 68 Newton meter, because you see this factor of safety factor is always given. So that's what you see now we have we can absorb the energy, or we can store the energy up to 68 Newton meter to avoid the failure. So strain energy density, you see for with that particular basis, now we have the volume of the rod is V, which is A into L, or we can say that pi by 4 d square L. So now you see we know that the diameter is given already and the length is given. So by keeping those things, we have pi by 4 into 20 into 1.5 into 10 to the power cube, because you see we have it is in the meter. So now after converting those things, we have 471 into 10 to the power into 1000 millimeter cube. Our main aim is to calculate, you see, the yield strength. So as we know that the modulus of resilience is equal, because you see now we are keeping up to only the elastic region. So for that, whatever the energy is coming, it is coming in terms of the modulus of resilience. So it is equal to the strain energy density when the maximum stress is reaching up to sigma yp. So u is equals to sigma y square divided by 2e. We can say that since u, which we have already calculated in that particular term, is 0.144 is equals to sigma y square divided by 2 into 200. The E is given as 200 gigapascal, so 200 into 10 to the power cube. So after calculating that part, we have sigma y, which is equals to 200 megapascal. So we have now the yield strength which is being calculated on the basis of modulus of resilience, and it is coming as 200 megapascal. So now you see we would like to conclude this chapter, we started with the strut, which is having, you see, the pin joint and consideration of the eccentricity. So we got to know that eccentricity is a key phenomena which we were ignoring at the time of Euler theory. So that's what you see. After consideration of that part, we found that actually we are pretty close to the real experimental values, and they are exactly somewhat matching, because here also we are considering the additional bending moment is there, and due to that certain kinds of curvature part is. So we started with that part, and then we found that some of the energy associations are there when the material is being subjected by a kind of loading. So we started with the strain energy, that what exactly the impact of the strain energy is there when the load application is. And the second part was coming as the modulus of resilience, when you see the load application is there, and we are only keeping up to the elastic region. So this modulus of resilience will give you the energy absorption by the material when the load application is there up to the elastic region, and whatever the energy is coming, that will clearly defines the limit of the elastic region. And then you see the last part was there, the modulus of toughness, in which we are simply going up to the failure part, and whatever the total energy which is being absorbed till fracture or the rupture is always known as the the modulus of toughness, and it is simply gives you that how much energy a material can withstand up to prior to failure. So these three the energy terms which we discussed in that particular way, but in that you see all these things are there under the simple action of loading. And then you see we discussed lastly about the two numerical problems that you see how we can calculate those parts, especially which is based on the strain energy and based on the modulus of resilience. Now in the next lecture we would like first discussed about the strain energy in the bending part. Means when you see the bending actions are there, then what exactly the strain energies are there, and what how we can calculate those part, and then we will discuss about the numerical problems associated with the strain energy. Thank you. Thank you.